Suppose if you have Q1 and Q2 and then you already started your measurement. So you are trying to measure this capital F, that is the force between the two charges. When you are doing the measurement, suppose I bring another charge Q3 here, I will keep it here. If you do that, will the force between Q1 and Q2 change or not? That is the question. The force that you are going to calculate between these two charges will not be altered because of the Q3. So the conclusion is that if you are going to bring a third charge like this, and if you are going to place it in the vicinity of the two charges Q1 and Q2, then the third charge that you brought will not affect in any way the interaction between the first two charges. And this is very important result, that any additional charges that you are going to bring in the place where you are doing the experiment will not affect the original interaction. Suppose if a fourth charge is kept here, then even then this Q3 and Q4, both of them together cannot change the force between Q1 and Q2. And we are going to say that this conclusion is known as the superposition principle. So the superposition principle says that the interaction between a pair of charges will not be affected due to the presence of additional charges that are surrounding the pair of charges. Q0 with Q2 is one pair. Q0 with Q1 another pair. Q0 with Q3 another pair. Like this you have to form each pair and then you have to complete with all possible available pairs, and if you add them, then that expression will give you the total force acting on a particular charge that you have chosen. So we are going to say that this is some kind of a test charge. The Coulomb's law obeys the linear superposition principle, and that is the ultimate conclusion that we have. So based on the explanation, now we can write down what is the total force on a particular charge capital Q because of the presence of several charges surrounding capital Q. The total force acting on the charge capital Q will be equal to the constant being the same for all the expressions. We don't have to repeat them. So let us write down something common here. 1 divided by 4 pi epsilon 0 into. So this is the common thing we can write down. And then you can write down the Coulomb's law pair by pair. That means let us say that, let us consider the first pair Q1 to Q. So in this direction I am saying. So which means that the Q1 will be exerting a force on Q. So that is the direction I have written. So for that, how do you write down the expression here is that you can write down that Q1 divided by, it doesn't matter whether you write Q1 first and capital Q later. So that is not important. Only this direction is important. Then we can write down divided by, you don't have to show the subtraction of which vector to which vector, because that will come if you draw the origin. So you have to draw some origin somewhere here. Okay, let us say that you choose some origin here and from there you draw all the things, then automatically the subtraction between two vectors will come. So for the time being, I mean symbolically, for this diagram you can write down that this is an R1 square, and remember that we are using the script R here, and only one suffix is enough. You don't require two suffixes. I already told you in the last class that in many books you can have R12, R21, etc. So two of the scripts, I mean subscripts are there, and you can avoid two subscripts and you can keep only one of them if you are going to have the idea of having a separate symbol for the test charge capital Q. So that is the point that I explained in the last class. So if it is the case only one suffix is required, so you have an R1 square where R1 could be this one. So that is the vector that you have. And if you want to show exactly how to subtract the vectors, then you can always draw like this and then find out. So you don't have to draw for everything. We are now explaining based on this diagram for understanding what is the Coulomb law, and once that is clear, then you can repeat this kind of triangle. For each one of the pair you have to repeat this. So this is how you can repeat. So as it is clear, you can understand what is the meaning of R1 vector, where the arrow is in this direction, and correspondingly you can choose the origin and then find out what are the two vectors that you have to subtract. So that is the expression that I have written. And once this is over, the important point is that this particular force will act in the direction of unit vector along R1. Which means that there is a unit vector. So unit vector means I can draw any parallel to this. For example, this is a parallel that I am drawing, whose length can be 1. So this yellow color arrow will represent a unit vector corresponding to R1. Or you can write here. It doesn't matter where you draw. The direction should be properly there, and then its length should be 1, and that's all about it. Whether you choose this vector or whether you choose this vector, that is not at all a problem, because everything is parallel to this script R1. And that is what I have written here. So I will say that this is R1 and then put a cap here. So that is your first unit vector. Then plus, you get a plus. Then come to the second pair. Second pair, how do you write? That we can write like this: Q into, then you have a Q2 divided by R2 square, and similarly you have an R2 cap, then plus, etc. And the last one you can write down as Q into Qn divided by Rn square, and then the corresponding unit vector will be Rn cap, and then close this bracket. And I will erase the other unwanted things. And that is what you are going to have. And as you can see, even though the equation looks simple, the difficulty lies like this. R1, you see this R1 unit vector, this R2 unit vector, and similarly R3, R4, etc. several of the unit vectors, and finally this Rn unit vector, they are not parallel. They are not parallel. As you can very easily see in this particular configuration itself. If this is your Q2, for example, if I am going to draw a line like this, Qn to capital Q, if this is the direction of the force, then correspondingly unit vector will be in this direction. So that would be the unit vector corresponding to the Rn. That is the unit vector. So what is the understanding? Our understanding is Rn unit vector and R1 unit vector. Let us say that this yellow one, this yellow color one, which is representing the R1 unit vector and Rn unit vector, they are not parallel. So similarly, all the n number of vectors that you have, they are not at all parallel, and therefore vector addition has to be applied in order to find out the new direction. I mean the final direction of the combined force. So that requires considerable amount of algebra has to be done, but this is the point to be noted, that all the vectors are not common. So even though you say that it is superposition, this is where the little difficulty comes because of the vector. If it is simple scalar, simply you add them and the job is over. Well, fine. So this is exactly whatever you have written is known as the principle of superposition. And then we will do some problem based on this, because numerical problems are basically emphasized for the undergraduate students when compared to graduate studies. When you are doing the graduate studies, at that time also you will be solving problems, but numerical problems are minimized. At that time you will be studying theoretical problems, where you keep variables and then find out the solution to a particular problem. So now at the undergraduate level, you will be dealing with numbers. Numbers means consider 1 millicoulomb, or you consider 10 nanocoulomb of charge, let the distance be 10 centimeter, like this. Numbers will be given, and then you will have to evaluate these vectors. Because dealing with numbers, that requires some practice. If you think that what is there in that, simply take all number and substitute here. In principle, it's correct. You have to take the number and substitute. But in practice, what happens is that a large number of it is very easy that you will be making several mistakes before you arrive at the correct answer. So that's why the problem section is very important. And remember that for you are going to have 2 problems in the end semester examination, as you already know, because you know the overall idea about the questions. So you'll be having 3 questions for your final semester examination, and question number B and question number C, that will be problems. So that is why you also be careful that some practice on the solving problems is very important, and this one will be something like a standard explanation of some of the theoretical part or deriving some expressions, and such kind of problems will be there on the part A. Whereas the B and C, you'll have to choose two problems will be there, and you will be given a choice of solving any one of them. So you should be familiar with solving numerical problems. Okay, so that point we will come back to this point later. So our conclusion is the following, that whatever we have discussed till now, you should remember what is the objective of our discussion today. Our objective is to know whether the Coulomb's law itself is valid under certain conditions, or will there be a situation where the Coulomb's law will break down. That is our today's objective, and on the way we have got the certain result, and that result is what we call as the superposition principle. And then we make a statement that Coulomb's law is Coulomb's law is still valid even if more than two charges are present in the system. So this is the first important conclusion. Even though this is one conclusion, I have written down as subdivision 1 and 2 because when you are asking a question and getting the answer, you also got one principle or one particular conclusion you got, which is widely applicable, not only in the case of the Coulomb's law. So that is why I have written it as a 2 subdivision. So this is one of the main conclusions. The second question that is asked or that is raised on the Coulomb's law is that the power 2 means we are talking about the inverse square law. You see that the force that you are going to write down, that it is inversely proportional to 1 over r square, where r is the generic distance. No, we are not talking about what kind of symbol that we have. Generic distance means the distance between the two charges, and that's all about it. So the question now is regarding this 2. So there is a 2 here, right? So is this 2 that you have here is exact or approximate? By that what I mean to say is, we are asking the question whether the power can be exactly 2 or can it be 2.1? Why not like this? We can say that according to Coulomb law, we can say that the force is inversely proportional to, by the way, inversely proportional, I can attach a minus, right? So because 1 by r means r to the power minus. It can be like that, or it can also be like this. Force is inversely proportional to 1 divided by r to the power of 1.9. So this is a 1.9 here, and that's a 2.1 there, which means that we are now we are raising a doubt that the r square that we traditionally say the inverse square is really exactly 2, or it can be 1.9, or it can be 1.95. Is it like that? Because how far is the experimental accuracy is correct and reliable, that we can always agree that 1 by r square is valid. So we are asking the question, validity of r square is how accuracy it is. So that is one of the main interest among the people over the several years. So the history says very interesting thing, that right from the time of 1772 people have got this kind of question, and people started to do making measurements, for example, because everything is measurement. You have to perform experiment and then find out if there is any changes are there. So our objective is very clear. Now let me write down that our objective means our aim. The aim is that we would like to know, if you are going to write 1 divided by r square, if you want to write like this, we are asking the question, for this 2, what is the plus or minus of how much? So we are putting question mark here. So that's a question mark. So 1 divided by r to the power 2, that's okay. Is exact 2 means plus minus 0 will be there, or will there be a small plus minus is there? So that is our objective or the aim of the experiment. And people have done, of course, starting from 1772 onwards, different people have performed experiment in order to address the answer to this question. And there are important main results. Everything say the same thing. Of course, the result doesn't contradict. Okay, all the people got the same conclusion. Let us see what is the conclusion. I'll tell the main places where there is a considerable accuracy improvements are there. Only that time I am writing. So one is the 1860, and interesting years are 1860 means remember it's Maxwell period. When I write 1860, immediately remember that it is a Maxwell time. At the time, Maxwell time means the time when Maxwell has proposed the mathematical theory of electromagnetism. That is the meaning of Maxwell time. And 1772 is roughly, it is the same time as the Coulomb law itself was proposed. So that is the period. So what is the main conclusion during this period is that the value of 2, now remember that we are going to discuss on this part. So let me therefore highlight here in another color, for example. So only yellow color I am now showing that 2 plus or minus of how much. So this is the question. I'll write in big letters, 2 plus or minus how much. So that is the question, and people have obtained interesting answers here. In 1772, the result says that the power 2 has an error of plus or minus 0.03. And power, remember, power doesn't have any dimension, right? It is just squaring the distance. So when you're taking a square, is it exact square or should I take 2.03? The meaning is the power can be anywhere between 2.03 to, if you are going to subtract 0.03, I will be getting 1.97. So that is the kind of power. So you can have 1 divided by r to the power of 1.97 to 1 divided by r to the power of 2.03. That is the meaning of the conclusion. And this plus or minus value is obtained based on repeated experiment. You keep doing the experiment several times with several different distances. Not only one distance, you should not repeat the experiment. You have to repeat the experiment for various types of distances, and then you have to ask the question how accurately you measured the distance. Because this plus or minus is coming from the distance measurement. So if I am going to consider the first charge and the second charge with a distance, say 1 kilometer, for example, I'll say 1 kilometer. The question is, how accurate is 1 kilometer are you measuring? Did you measure to high accuracy, or what is this plus or minus here? So that question comes into picture, and based on how accurately you measured this particular value, so the number 0.03, it reflects. So like that you have to perform the experiment. So we are not going to those details of how to perform the experiment, but overall that is an idea. So based on the accuracy of the other parameter that you are going to fix in the experiment, ultimately the power law accuracy comes into picture. Ultimate conclusion is very clear. So what is the conclusion from this? The conclusion is that the inverse square law is exact only. Even though 0.03 is there, 0.03 came because you have some error in the measurement of the distance. No, this distance you have, right? There is a considerable amount of error in the measurement of this, and there is a measurement error in the f, because ultimately you are going to measure f here. So there is an error in the measurement of f. So because of these two errors, ultimately all the error is dumped on the power that you have. So that is why it is the 0.03 is coming, but otherwise this power 2 is going to be exact. So that is the conclusion. But as time changes, people want to verify, or people want to increase the accuracy or precision of whatever they are speaking, and therefore in 1860, again a similar kind, not identical experiment, people try to improve by various methods, and therefore in 1860 the people have done the experiment, and interestingly the result says that the error is plus or minus 10 to the power of minus 6. So 10 power minus 6 means you can see 0. Okay, you write 0.1, 2, 3, 4, 5, 6, 1. That is the meaning. So you have a 2 here. So that is the meaning of this one. So in 1860, this is the result they got. This result is coming because you have an improved way. You have a better way of measuring the distance. You have a better way to measure the force itself. So when you are improving the experimental accuracy of the measuring devices, namely the force and the distance, naturally what happens is you got this particular error is very small, which means that the the ultimate conclusion is still the same, that the power law, namely 1 over r square, is exact only, and still the small error is present again due to the errors that are propagated from the measurement of the force and the measurement of the distance between the two charges. So the interest further continued even after this, and the main result is in the year 1983, where the result is much more interesting, and it is really astonishingly, the error is very small, and as per the experiment the value is given by the power is 2 plus or minus 10 to the power of minus 16, and that is the best that is possible by the experimental methods. So the power, you remember that this is power, not the distance. So the power doesn't have any dimension. So you can easily see that the power is not at all varying by 1 part in 10 to the power of 16, and that is the greatest really very high level of accuracy that is already obtained in the year 1983. And therefore the conclusion to this question is clear, whether the power is an exact power or is an approximate power. So the conclusion is that it is an inverse square law. Therefore we can properly say that it is an inverse square law, because if it is 1.95, for example, we cannot say square. Square is not 1.25. Square means you have to keep exactly 2 here. So if this is r to the power of 1.95, this one we cannot call it by the name square. So that is the reason why people ask this kind of questions, and then our conclusion is that yes, it is exact, and we can very well call this particular expression or the law as an inverse square law. So this is the second question. So here I have written that the second question raised on the validity of the Coulomb's law. So that is the second one. So the next one is the another question that is really interesting in terms of the size of the charge. So let me write down the third one. So question number 3. So this is the question that we are asking, a simple question, that when you are performing the Coulomb's law experiment, which means that Coulomb's law experiment means simply you put a Q1 here and keep a Q2 here. So you have two charges Q1 and Q2 which are separated by some distance. The question is how big. Simply we are putting a dot here to say that there is a charge present at that particular point. But in the experiment, remember, we cannot have a point charge. You can't have a point for an experiment. Basically, experiment is done with some object. You take some object. The object can be cylindrical in shape or spherical in shape. So there is the size and the shape of the object comes into picture when you are performing an experiment. You can't take a dot and then do an experiment. So that is why these questions are coming, and we are interested to know, suppose if you take a larger object. So suppose, let me say that you are going to take an object like this. I am just drawing an arbitrary shape here. It is neither a sphere nor some kind of a cylindrical structure. Nothing is like that. Some kind of a stone. Let us say you take a stone, for example, and it is occupying some space. Now, what is the meaning of saying that is, I have drawn a little bigger like this, is that it is occupying some space. That is the meaning of that. And let us assume that this particular big object is charged such that the total charge on this particular size, this particular big size object is Q1. And similarly, you can have another possibility that I can have another material or another object of this particular size. Of course, the shape is it will keep changing, but let us assume that this is again an arbitrary shape. But then the total charge is Q2, because this is the only thing that is possible in an experiment. In an experiment, you always take an object. That particular object will occupy some space, and it will have some shape, or it may not have well-defined shape. This is how the experiment can be performed. You cannot say that I will be taking a point charge like this. because on a paper we can say that you put a point and say that this is Q1, but in reality you can't do like that. And therefore, when you are doing an experiment like this, whether the size of the object, this is called the charged object. We say that these are the charged objects. So whether the size of the charged object will influence the validity of the Coulomb's law. That means, suppose if I take very small object, the Coulomb's law may break down, or if you take a very big sized object, Coulomb's law may break down, whether anything like that is happening, or that you can take any sized object and still say that the Coulomb's law is valid. So what is your conclusion? So that is the question, and people want to do experiments on this. But however, there is an interesting point here. Without doing the experiment, you can think about how to proceed for this particular answer. So the answer comes like this. When you write down that f is equal to some constant, okay, constant we can write down later, and we have an expression like this, q1 q2 r square, and let it be a scalar, no need to worry about the vector here, and then some constant is there. Forget about this. Now, what is the place where this equation will have connection to the size of the object? Q1 itself doesn't enter into size, because we are saying that the total charge of this particular material is Q1. That's all. So irrespective of how big or how small the object is, Q1 is going to be the total charge. Therefore, in this place, nothing will happen. So let us not worry about this. So I am cancelling this. Then come to the Q2. The same thing is applicable here also. Therefore, the size of the object or the shape of the object will not affect when you are substituting Q2 in the equation. Okay, then next come here. In the place of R, so what is R there? So that is a question you have to think. What do you mean by R? The answer says that it is the distance between the two objects. Then you ask the question, how will you measure the distance? So therefore, the doubt now comes, how do you measure the distance? So shall I take a point here and then draw a line like this? For example, I can draw a line like this up to this. So shall I make a measurement like this from here to here? Is this correct? And naturally you yourself will tell that this is not correct. The reason is, you will ask a question, why did you choose this kind of point? There is a point here and there is a point here. So between these 2 points I measured the distance. So is this the distance? You are asking the question, and you yourself know that this is not an acceptable one. Because you have to now explain, why did I choose this particular line? I have put it in pink color. Okay. So then naturally what happens is, people will have a tendency to say that, okay, why don't you choose the center of gravity? See, for every object you already know how to calculate the center of gravity, or even no need to calculate, even you can find it from an experiment, how to determine the center of gravity of an object. So let us assume that the center of gravity of the object is at this place. I am putting in yellow color. So you must be able to see that this particular dot in yellow color, I am now drawing it in bigger size so that you can see. Similarly, you can find out there will be a center of gravity at the yellow color dot which is there, and then you will say that, okay, you draw a line between them. Drawing a line between them means basically you are measuring the distance from these 2 points. Basically in experiment you have to measure like that. That is the meaning. So you want to say ultimately that this kind of an yellow color point will be the center of gravity. So this is the most probable way of thinking. Where can we consider the center of gravity of the 2 objects as the points that we can consider, and then you measure the distance between them. Now once that fixing is clear, then measuring the distance is not a problem. You can accurately measure the distance by whatever technique available. The question is whether to choose the yellow color dot here or the pink color line here. Which point we have to choose? That is where the question comes. And now here you have to be more careful, that ultimately our answer says that center of gravity cannot be accepted. You cannot consider the center of gravity as the point to measure the distance between the 2 points. And therefore you cannot take the 2 yellow points also into consideration. So natural question is, why center of gravity is not applicable? The answer is also once again simple. You have to again understand the meaning of center of gravity. Center of gravity means how the mass is distributed. See, when you are taking an object like this, you say that the masses are distributed. It is like this. You take some sand, for example, go to the beach, take the sand, and then mix it with some kind of gum or glue, and then you just make it in a form of a sphere. Then all the particles, namely the sand particles, will stick to each other so that it becomes some kind of a spherical shape. It need not be spherical exactly, whatever shape it comes. So you understand, then ultimately you understand what do you mean by an object. An object contains small particles which are all held together by some kind of force. And here we have applied gum or the glue, so that is what is holding. So you understand that a larger object means there are some minor small particles that are distributed. And therefore, the center of gravity is based on mass distribution. What is meant by mass is that the small particle, one sand particle will have a mass m1. The second sand particle will have a mass m2. Like that, you have taken something like 10,000 sand particles and then you made it as a spherical ball. Therefore, m1, m2, m3, that are the different masses which are distributed in different places. Distribution means all the sand particles cannot stay at one place. If one sand particle is located here, the second sand particle can be located at least here. Suppose if this is the first sand particle, this can be the second sand particle. I'll put the second sand particle in the pink color, so you can see now that would be the second particle. You cannot keep the second sand particle on top of the first. I mean, on top of the first means exactly in the same place. You can't place it, because in that case you have to push the yellow color particle. So therefore, that is why we use the word distribution. They are not located in the same place. So the mass distribution is what you are going to use in order to determine the center of gravity. And therefore, now in our problem, there is no mass distribution. We are not interested in the mass. We are interested in the charge. Therefore, we have to consider the charge distribution rather than mass distribution. Therefore, if you are going to think about the mass distribution and do the calculation based on the center of gravity and then calculate the R according to this idea, then your measurement of the R will be wrong, and therefore anything that you use it in this particular expression will also go wrong. So the conclusion therefore is very clear that you cannot use big sized objects for the measurement of force between the two objects in the case of Coulomb law. You can measure, but that's not a problem. After measuring, you can't compare with this equation and tell what is the value of R. Experimentally, you can always measure and find the force. That is not the point. The point that we are asking is what value of R should be here in that experiment. That cannot be precisely explained. And therefore, whenever you want to perform the Coulomb's law experiment, don't take an object of larger size. Larger size, by larger size, what do you mean is anything which occupies a considerable amount of size. So the question comes, how do you define this big and small? So that is really, one has to think, what do you mean by big? What do you mean by small? Okay, how small is small? That is the question. So once you understand that, then we can go ahead and then perform the experiment. So the idea clearly it's not difficult, but if you think for 1 minute, you can get the answer. So if you are going to consider this object, for example, let us say this particular object, let me write down what is the dimension of this. So in order to get the dimension means order of size. Now you can measure what is the size here. Let us assume that this is 1 centimeter. It doesn't matter whether you measure from left to right, top to bottom. It is a rough estimate. Here the accurate value is not at all required. Okay, if you measure from the left edge here, this is the left edge to the right edge, I am getting 1 centimeter. If you measure from the top edge to the bottom edge, that is, this is the top edge to the bottom edge, if you measure, you may get 0.7 centimeter. That's okay. Those small numbers, it will not affect. So this is we say that this is the approximate. We say that roughly it is the order of estimate of the size of the object. So this is the size of the object. Not an exact value, but if it is of the order of. And similarly, you do the same kind of size measurement here, from somewhere here to somewhere here, from edge to edge. You measure and then find out what is its size. And probably you can say that this is something like 2.1 centimeter. Let us assume that this is the situation. Then after this, what you do is you find out from here to here what is the distance. This distance, that means the what you call the place where the object starts, so that kind of a place, and then here also the place where the second object starts. So anyway, these are rough, these are not accurate values, and therefore we need only estimate of that. Okay, so if you are going to measure this distance, and let us assume that this is something like 15 centimeter, we will consider as an example. This is what happens in an experiment. So now what are the numbers that I want to consider? 15 centimeter is one number, 1 centimeter is another number, 2.1 centimeter is another number. So these two numbers are the numbers representing the size of the object, and this particular one is the distance separating them. All of them are approximate. Remember, none of them are exact. If it is exact, then there is nothing to discuss. Your job is over and there is no question at all. Okay, the question is how to fix the distance between them accurately. That is the question. So therefore, let us now discuss here. So we have 1 centimeter is one case, 2.1 centimeter for the second case, and then the distance between them is 15 centimeter. Now practically, how do you go about in order to get the answer to this question is that let us say that this is R. Let me say that this is R, and let me say that both of them can be called by some symbol D. D is something like diameter of the sphere. Even it need not be sphere. So D can be a symbol. Any kind of object, you can assume that it is spherical in shape and then take its rough estimate. Remember that these are rough estimate. You need not take 2.1. Okay, if you measure from, say, I will draw another line here, then you will be getting an idea. See, if I am going to draw a line here and then draw another line here, for example, then this distance from here to here, this may not be 2.1, it will change because it is not spherical object. So like this, you can take any measurement. It is only an order of accurate answer. That's all, not an exact answer. And therefore, we will say that this is D and this is R. So a practical way of getting the solution or practical way of dealing the situation is that you consider any distance. Let me write in white color. So you are going to put this particular condition now that if you are going to consider R to be much greater than, so like this you have to write two greater than, so you have to write close together, so that this is known as much greater than D. This is the condition. If this is the condition that you are going to satisfy, if R is going to be much greater than D, then the center of gravity can be taken. Then the center of gravity can be taken as the points. Point means what? The point from where you make the measurement. So this is the kind of a practical way. So practically what it means to say is, now 15 and 1, now what about this 15 and 1? Is it really good? It's not really good, because when compared to 15 centimeter, 1 centimeter is not far. Far is different, no? Just if you ask the question whether 15 is greater than 1 means you will always say yes. So this is the point that you have to note down. If you ask the question whether 15 is greater than 1 means yes. But if you ask the question whether 15 is much greater than 1, then you say that it is no. Okay, for a clear understanding, you think in terms of money. You have 1 rupee coin with you and you have 15 rupees. Two people are there. One person is having only 1 rupee with him. He doesn't have any other money. That's all, only 1 rupee. The second fellow has maximum only 15 rupees he has. He doesn't have any money at all. That's all. Now, only based on this comparison, can you say that the fellow having a 15 rupees is a very rich fellow? Can you say like that? That is the question that you are asking. So that is the meaning that we are going to implement for this greater, much greater than. Mathematically, it is greater than. That's what I have written yes here. This yes means mathematically it is greater than. Yes, that's fine. But can you say that 15 is much larger when compared to 1? You say that it is no. So the fellow having a 15 rupees alone, we can't say that he is rich. But suppose if this fellow is going to have 1.5 lakhs rupees, whereas this fellow has only 1 rupees, then we say that yes, the other fellow is rich. That is what that is the concept that you are going to use in order to check the much greater than that. So which means that typically if you are going to perform an experiment like that, you can always consider 1500 centimeter can be considered to be much greater than a 1 centimeter. It is up to you. There is nothing like you are going to fix this number. See, you are going to do the experiment. So what is the suggestion coming from this lengthy discussion is, since you are going to do the experiment, why do you want to fix at 1500 centimeter? If you believe that 1500 centimeter is not much greater than, then why don't you go to 15,000 centimeter? That is the meaning. So it is you who are going to decide. If you don't believe that 1500 is not considerable, then go to 15,000 centimeter. Now certainly you have to agree, right? It is certainly agreeable. 15,000 centimeter is much greater than 1 centimeter. And when you are making this kind of an experiment, the conclusion says that this is the conclusion. The center of gravity can be taken as the point. That means it can be taken as the point rather than an object. So instead of having an object like this, you just consider it as a point, and the point can be the center of gravity. That error will not come. Error means mass distribution versus charge distribution. Error will be minimized. Ultimately, what is happening is the error is getting minimized, and therefore the formula that you are going to use, Q1 Q2 divided by R square, will give you an accurate reproduction of the experimental value. That is the conclusion. So the conclusion can be therefore written like this. So instead of saying all this lengthy discussion, our conclusion says that the Coulomb's law and that's all. That is the conclusion. So ultimately what do you want to say is that the Coulomb's law is valid only for point charges. But again you are going back to the old school. Just now we said that point charges are not easy to do in an experiment. That is why we are taking in a larger object. And again you are coming and saying this means ultimately we have to understand like this. Whatever you have written here, namely Coulomb's law is valid only for point charges, is understood. That's what I am going to write like this. So that is what it means. So the Coulomb's law is valid only for the point charges means in practice, that means when you are performing practicals or an experiment, the understanding is like this. If the distance between the separation or the separation distance of the two objects is much greater than d, where d is the diameter of the finite sized object. Finite sized means not a point object. Point object means the size is 0. Finite means not 0. It is slightly greater than 0. That is called a finite sized object of diameter d. If you are going to consider this kind of criteria and then performing the experiment, then we will treat or we will consider that you are really making use of point charges in the experiment. That is the meaning. Even though you did not take the point charge in the experiment, we can still treat, we can still consider that you are taking only the point charge because you are satisfying this condition. Like this, we have to interpret the meaning of this particular sentence, namely that the Coulomb's law is valid only for point charges. So this is the conclusion for this particular question. So you have the question here that I have written that this is the third question that we are discussing. How big or how small the charged objects can be in the Coulomb's law experiment. That is the question. The answer is clear, that provided that the separation distance is much greater than the size of the object, you can always consider the extended object. Extended object means finite sized object as the point charge itself. That is the conclusion that we are making. So in the list of validity, we have been discussing on the validity of the Coulomb's law, right? So we have seen 3 of the possible questions, and the 4th question that is possible is that over what range of distance the Coulomb's law is valid. So you can understand what do you mean by this range here. The range is the R that you are going to use in the equation. Range means we need a minimum value and we need a maximum value. So R is the distance in the Coulomb's law, and you are asking the question, you tell me some maximum value of R. So I will write it down as R maximum. And you also tell me some minimum value of the R. So I can write it as R minimum. That means I have a minimum distance between the 2 charges and I have a maximum distance between the 2 charges. Only in between these 2 minimum maximum values, your Coulomb's law is valid. Is it so? I am not saying this conclusion. It is only a question now. I am explaining what is the meaning of range, because range is written here. Range means there is a minimum value and maximum value of the distance. Between that distances only the Coulomb law is valid. If you are going to go outside of this range, Coulomb's law will break. Is it so? That is the question. We don't know the answer. So the people have to do experiment. Remember once again, you can't substitute. You see, if you are going to take only mathematical discussion, then literally you can substitute any number you like. You are going to have an R square, forget about the vector here, and R can be any number. You put 0 here. If R is equal to 0, then I will be getting force equal to infinity. Mathematically it's possible. You can substitute 0 and say that F is infinity. But we are not asking that. We are asking if you are going to perform an experiment in such a way that the distance between the 2 charges Q1 and Q2, so let me say that this is your Q2, if that distance you keep reducing and go to a small number, let us say that I will go to a small number like 10 to the power of minus 5 meter. So if I am going to reduce 10 to the power of minus 5 meter is one possibility. You finish the experiment and then repeat the experiment for 10 to the power of minus 6 meter. Finish it. Do the measurement for minus 7 meter. Like that you keep on doing the experiment for smaller and smaller distances, and when you are doing the experiment, you have to tell me after finishing the experiment whether the Coulomb's law, namely the whatever equation that you have written here, this is what I mean by the Coulomb's law. So do you believe or are you observing this particular equation valid for all these distances? That is the question. Suppose if your experiment and the calculation don't agree, then you say that the Coulomb's law breaks. And one thing that is very clear when it breaks is that something that is trivial, that R equal to 0. So certainly if I substitute R equal to 0, it breaks. And through an experiment, how do you understand R equal to 0? Is it really possible? You have to think, can you perform an experiment with R equal to 0? Mathematically I can substitute. Now R equal to 0 means, what is the meaning? This is your Q1 and that is your Q2. So the Q2 has to come in the same place as the Q1. So can you place this particular Q2 and then keep it exactly on Q1 itself? That means on Q1 is different, at the same place is different. On Q1 means there is a distance between them. You have to be very careful. On is different and exactly same place is different. It is, if you want to understand a little better, you think that in the classroom you have 2 chairs, for example, and in the 2 chairs 2 of the students are sitting. So if a third person comes there, where will he sit? He can't occupy the same chair. That is the meaning I am trying to say. Okay. If you want to occupy the chair, then one fellow has to move. So similarly, if this charge Q2 has to be kept in the same place as the Q1, then the Q1 has to move. If Q1 is not moving, then Q2 cannot come there. And if Q2 cannot come there, this R equal to 0 that you have written is not possible. Therefore, even though you can tell mathematically R equal to 0, in an experiment R equal to 0 is something that is not at all possible. So you simply forget about it, it's not possible because you cannot keep two objects in the same place. One object will occupy some space, that's all. Second object cannot come there. If the second object has to come there, the first object has to move from there. So therefore, R equal to 0 possibility is rejected. So the next possibility, okay, if 0 is rejected, then okay, next what is possible? So the next what is possible is, you can consider any number greater than 0. That's the meaning. You take any number slightly greater than 0, everything is possible. And if it is greater than 0, then where is the limit? So the maximum limit can be, you can write down that the maximum limit can go all the way to infinity. It can reach infinity. Okay, ultimately you can go to any distance which is as high as infinity, a largest possible number. So these are the possibilities that one has to explore in an experimental way. So this has to be done experimentally. Okay, the answer doesn't come from mathematics. So people have done, now in order to answer this question, people have done several experiments and there is a clear conclusion. Now we have the conclusion, so you don't have to struggle to do any experiment. It's already done and we have the conclusion like this. The conclusion says that if the distance between the two charges R is less than 10 to the power of minus 16 meters, then so this is the first conclusion that we have, that you can always have the distance between the charges greater than 0. I have written that this is greater than 0. Okay. And here we have written that this is 10 to the power of minus 16. So remember that 10 to the power of minus 16 means it is greater than 0. So 10 to the power minus 16 means greater than 0. So therefore, when the distance between the separation is less than this number, Coulomb's law breaks. Breaks means, what is the meaning of breaks? Means the measurement and the calculation don't agree. Calculation says that you do the Q1 Q2 divided by R square, put the numbers here and then do the calculation and then find out what is the number in your calculator. That is very F. Okay, and the constant of proportion, whatever you want, keep it. And then you have an experiment and then you have performed an experiment and from the experiment you also have the value F. So I am writing F experiment, this is F calculated. Now what this means to say, what is the meaning of this break is that F calculated value won't agree with F experiment value. It will be totally a different value. That is what is the meaning of breaks. Breaking means this particular equation is no longer valid when the distance between the charges is any number less than 10 to the power of minus 16 meter. So this is the first conclusion. And interestingly, if you see what is this number that you have 10 to the power of minus 16 meter, what is that? What is that number exactly signifying is that you can easily understand if you know the size of the nucleus. So let me now write down that if you are going to have an atom, for example, so if that is an atom, roughly I am drawing like this, and then if you have a nucleus, for example, so that is a nucleus and that is an atom, and let us assume that the electrons are there inside this revolving, whatever it is, and this particular nucleus, the diameter of this nucleus is approximately 10 to the power of minus 15 meter. And remember that this is the nucleus I am talking about. This is the nucleus, and the entire the outer circle that I have drawn is the one corresponding to that single atom. You can consider it as a single atom. So for this one, the diameter of this particular one, the outer, I will write outer. So diameter of the outer sphere, let us assume that you draw a proper sphere, for example, then the diameter of the outer sphere is of the order of 10 to the power of minus 10 meter. So you need to have a feeling of the number, otherwise you don't know what kind of number it is. So when the distance is something like 10 to the power of minus 10 meter, it means that we are talking about the size of the atom. Okay, so if I am going to draw any line that, for example, from here to here. So if this is the one that I am going to draw, and that is what we mean to say this is D, and this is let us say this is D inner. So inner means I'll put I here. Okay, so this is the inside circle. So the inside circle, what we say, the nucleus, for example, the outer one being the atom. So 10 to the power of minus 15 meter means, remember what it means. It means you are the nucleus. And now remember, when the Coulomb's law is not valid, 10 to the power of minus 16 meter means it becomes invalid. The Coulomb's law is invalid. So what is the meaning of this particular number 10 to the power of minus 16 meter? It means that the distance is less than, or we say that it is smaller than. If we don't want less, we can say that it is smaller than nuclear size. Smaller than nuclear size means it is something like you are going inside the nucleus. No, that kind of small one. You should not come outside the nucleus. That is the meaning. If you come outside the nucleus, certainly the distance is greater than 10 power minus 16. So if one charge Q1 is here, and if the second charge Q2 is here, then the distance between this Q1 and the Q2, it has to be less than 10 to the power of minus 16 meter means, what is the meaning? You have to think carefully. The meaning is that the two electrons will be inside the nucleus. That is the situation. Two electrons are not there in the nucleus. That you already know. Okay. But however, we are not going to nucleus and then doing the experiment. You are now in the laboratory, not inside the nucleus. In the laboratory, we want to keep the two charges, one charge here and another charge here, such that the distance is less than 10 power minus 16 meter. That is what we mean to say. We are not saying that, okay, go inside the nucleus and do. So I am telling that the order of magnitude will be helpful to you. You can think about what kind of number it is. So when such small numbers are coming into picture, the Coulomb's law is invalid. Or invalid means this particular force doesn't work. The reason is that much stronger force comes into picture when you are going to such smaller distances, and they are the nuclear forces. Then coming to the higher side. So this is for the smaller side of the this is what we say the smaller side of the distance. I'll say that this is your R minimum. This is your R minimum. What about R maximum? So to get an idea about the R maximum, for example, people have done several experiments. Means what? R equal to 1 kilometer, for example. R equal to 2 kilometer, R equal to 3 kilometer. For each of these distances, people have measured the forces, and then they compare with the equation 1 divided by R square, and they found that everything is in agreement with the equation. Okay, that means the Coulomb's law is valid for all these long distances that you have. So ultimately, if you see the historical calculations and experiments that people have done, so people have done up to R equal to 1 lakh kilometer. So up to 1 lakh kilometer they have done, and even for this 1 divided by R square is working correctly. Okay, multiplication by constant, that's fine. Q1, Q2 will not change, and 1 by 4 by epsilon naught will not change. So when you are varying the distance, only 1 by R square will change. And the conclusion is that whatever be the distance that you are going to consider on the higher side, lower side you finished, okay, higher side. On the higher side of the distance, up to 1 lakh kilometer people have measured. You can ask the question, why they stopped at 1 lakh? Why don't you go for 10 lakhs or 100 lakhs? Okay, the answer is quite simple, that if you are increasing this particular distance like this, remember that this 1 by R square is basically 1 divided by, what do you mean by 1 lakh kilometer? 1 lakh kilometer means this is 10 to the power of 5 meter. So that is the 10 to the power of 5 meter. Then you have an R square. So that will be the order of magnitude for the force. So that goes like 10 to the power of minus. So this is 5 and 5, so 10. 10 to the power of minus 10. And remember that there is a k is there, q1, q2 is there. Let it be there. Otherwise, you will get a doubt on the dimensions. So something like this, then you have a k, okay, whatever it is, you this has to be multiplied by k. Then you have a q1, q2. Then you have so many newtons you will be having. Okay, so what I'm trying to say finally is that when you are increasing this distance from 1 lakh kilometer to, if you want to continue for, let us say, 100 lakh kilometer, if you want to continue, what will happen? What will happen is that this is becoming a small number. It becomes a smaller and smaller number. 2 times I have written smaller in the sense that if I repeat it for 2 lakhs kilometer, then the next number will be much smaller. If you repeat it for 3 lakhs kilometer, the number will be much smaller. So like this particular force will be keep on decreasing. So what happened finally is that, what is the reason for almost stopping at 1 lakh kilometer? Why they stopped is because when you reach the distance of 1 lakh kilometer, this particular number, whatever you have here, that force, that itself is practically, it becomes zero. Approximately, yeah. Because everything is practical, right? Zero means not exact zero. Practically zero. Your equipment will show zero. That's all. I mean, whether it is digital equipment or analog meter, there is no deflection in your meter means what will you do? It will be showing zero. So in a digital equipment, everything will be 0.000. That's all. That is the force. If it is the case, that's all. You can't do further experiment with 1 lakh kilometer and so on. That means you have reached to a maximum possible distance, namely practically our maximum has been done for 10 to the power of 5 meter. And they have done this, and the conclusion of the experiment is that the Coulomb's law is valid. It's valid. That is the conclusion. So interestingly, the higher side, namely the whatever maximum possible distance that you are going to travel, all along all those distances, the Coulomb's law is valid. The only place where the Coulomb's law breaks down is on the smaller side. 10 to the power of minus 16 meter. The Coulomb's law breaks down. The reason being that nuclear forces will take over. Okay, there is another force that will take over. Take over means their strength is much high. Okay, there is another fellow who is very strong. So if he is coming into force, that weak fellow has to keep quiet. That is what happens actually. So the electromagnetic force becomes a weak fellow in front of the nuclear forces. And that is why the Coulomb's law basically breaks down. So our conclusion is therefore clear for this particular question, that over what range the Coulomb's law is valid. The answer is this: the Coulomb's law is valid over a distance starting from 10 to the power of minus 16 meter less than or equal to, you can write R again, less than or equal to 10 to the power of plus 5 meter. So over this kind of a distance, the Coulomb's law is valid.